Hey, hopefully everybody can see this. Let me just double check on the chat. So, well, we're off to the second lecture for this week. We're going to be covering chapter 8. Before we get to that, let me just hit on a couple of admin points here. So next week, we are going to be back face-to-face, but we're going to continue to record these sessions, and I'll put them onto my page, which is right here, Lao sections 15 to 24. You see I have the chapter 7 video over here, and I have chapter 8 after I get done with today. I'll put that over here. You also see the two links to some conversions. So the decimal to binary, like I mentioned last class, that basically shows you a couple of methods. One is by subtraction and one is by division. Use whichever one you feel comfortable with. And then similar on the decimal to hex also. And you can also like do the mapping thing that I suggested last class also. So that's up to you. The recitations should be recorded, but you need to check with your TAs, right? So the TAs will be covering anything to do with the recitations, grading of the various things that you do, whether it's the assignments or the exams and quizzes and whatnot. So we'll be, breaking it up in that way, like I mentioned in class. So there are some people that are kind of joining the class a little bit late through add drop and whatnot. So not to worry. That's why we kind of put in like that first assignment, the introductory assignment, just to kind of be like extra credit. So again, coordinate with your TAs to kind of catch up on those things like that. Some of you probably saw the assignment for the numerical conversions. If there's any questions on that, make sure you speak to your TAs during recitations. I kind of mentioned it a little bit in the last class, doing stuff like addition and whatnot. So although it says numeric conversions, it's a little bit more than numeric conversion. You should be able to do like some arithmetic operations on it and stuff like that. Okay. So apologies if I'm not going to answer everything that's coming through on chat right now. I'm going to try to pick it up towards the end of class. And of course, I'll be staying after class. When we're doing this face-to-face next week, I will be staying in the lecture hall. That will be my office hours. So people are welcome to stick around after that, and we'll cover whatever you need. Okay. I might take a little bit longer on the first one because I can't really get in there right now. And I need to figure out how to present a lecture and also record a video at the same time. So I'm gonna probably monkey around with that a little bit. Let's see if I can get that figured out for the next class. But yeah, so anyway, here's this. And then just a reminder, here's the schedule. Here we are on week 2, and we're on to chapter 8. Your assignment posted, like I said, is your numeric conversions. And your TAs are there to help you in case you get stuck or you don't understand some of the examples that we put out there. Okay, so make sure you kind of get onto that. Now, one thing that I did notice, because some of you did the extra credit from last class, just remember, you can't submit for your assignment for numeric conversion. You can't submit a shared doc, right? And notably, when you start submitting like your program or for your assignments, you won't be able to use like shared docs and whatnot, because the TAs need to actually be able to download it onto their computer locally to run the stuff locally on their computer. Okay. Yes, the extra credit, try to get it in during this week. I do try to, you send it to my email, I do try to respond to the email. So if you don't see an email response from me saying thanks or whatever, I might have missed your email. So you can just go ahead and just ping me again. Okay. And like I said, what I do at the end of the semester is I take all of the emails and I basically just kind of group them together week by week. And then I look at the names, and then that's how I figure out, the people doing the extra credit. So if you kind of put your email like a couple weeks after the extra credit, it kind of screws things up a little bit when I try to group up the emails. Okay, so do try to get in by Sunday. That would help me a lot. Okay. Trying to think here if there's anything else from the admin stuff. Of course, pay attention to your announcements. I do try to make sure between myself and the TAs that it goes out to specific sections, so you don't get a whole bunch of these announcements like this. I know a couple of the TAs forgot about that, but most of the time I think we are focused on the messaging, so you don't get like, inundated with a whole bunch of announcements. So do try to pay attention to the announcements. Okay. All right, so let me try to pick up with the lecture here and go through that, and then I'll kind of get to some of the questions that are coming in to chat right now towards the end. Okay. All right, so let's get up to here. So it's chapter 8. This is basically how you store or represent various types of multimedia in digital format. Remember from last class, we talked about storing things on the computers as zeros and ones. Okay, so exactly how does that happen? And really from our perspective, what do we kind of need to consider or think about when we look at this? All right, so that's what we're going to go through. Yeah, these are a whole bunch of terms here. You probably saw it if you looked at the book. I'll try to hit up on as much of these as I can during the lecture. If I miss it, it'll be in the book for sure. And if you still can't figure it out from there, just give me a shout and I'll definitely clarify it for you. These are just like, multimedia. This is what we're talking about, right? So there's pictures, right? There's music or sound, however you want to look at it, and videos, okay? And you have something like this, right? And you might say, well, what the heck is this, right? Well, it's a bird, right? And it's like basically almost like made up of like these smaller images, right? So it kind of builds up to like this picture here, right? It's not exactly the same thing as how you might do it from a digitized standpoint, but it's pretty close, right? So I guess you can call it as an analogy, and you'll see what I mean in a second, okay? So just to kind of give you some kind of background, if you look at your computer, your monitor essentially, how does it represent an image on your monitor? Forget about whether it's a movie or something like that. There's this idea of like all these little dots, right? You can't really see them because there's like a gazillion dots there, right? And each of those dots basically will fuse together, right? These red, green, and blue, right? You see this red, green, and blue here, right? And depending on how you apply the strength of this red, green, and blue, they'll kind of blend together to make various shades or different colors of stuff, okay? So it's, and don't worry, we'll get more to it as I kind of talk through it, right? But the idea is that, it's almost like when you were in early school, like art class or whatever, you remember if you kind of mix different colors, like the primary colors, it will kind of come up with these other different colors, right? Now these colors on the computer, when you do RGB, doesn't necessarily line up with like how you used to mix colors, those primary colors with paints and stuff like that. But the idea is kind of similar, right? So you're mixing in these shades of red, green, and blue to come out with anything varying from black to white, okay? And then anything in between, okay? So that's what they mean when they say these dots, pixel, is a combination of these 3 color lights, okay? And then you have like a whole bunch of them like all across the screen, okay? So these 2 points are important, right? So black is the absence of light. And you'll see in a second, like each of these points will be like some number, right? So if let's say we're trying to represent black, when they say absence of light, you'll probably see like zero, not probably, you will see 0, 0, 0. Okay, so that's like 0 across the board for the red, green, and blue, and that's where you'll get black. Okay, and then white is the total opposite, right? It's the full intensity. So whatever the max number is. So let's say it's 255. Okay, so then you'll get 255, 255, 255, right? And that's the full intensity or maximum number, right? And then anywhere in between is some sort of gray. Okay. And yeah, I'm kind of talking about this ahead of like getting to some of the other slides, but that's the idea there. Okay. And so remember, what is a byte, right? There's 8 bits in a byte, right? So a bit is basically a 0 or a 1. It's just one single character, a 0 or a 1. And a byte is 8 of those, right? So it's 2 to the 8th, okay? And that gives you like a certain amount of information, right? So remember what I was saying in the last class. Let's say you have 2 characters, right? On a binary setup, that's 2 squared. That gives you 4 different combinations of values, right? It could be 0, 0, 0, 1, 1, 0, and 1, 1, okay? So that kind of tells you like how much information or how many different combinations of characters you can store, right? So 2 to the 3rd is 8. That's 8 different combinations you can get, and so on and so forth, right? It goes up exponentially, okay? So each of these, right? You remember I said the max is like 255, right? So 0 to 255. So a single color pixel is 3 bytes, right? So remember 255, 255, and 255. Each of those is represented by a byte, right? So 3 bytes, right? 1 for each color, right? Red, green, and blue. Okay, so that's 1 pixel, a single pixel, 3 bytes. Like I said, it's 1 for each color. Okay, right, and then if you have 24 bits, right, which is 2 to the 24th, it's going to give you this big number, 16,777,216 possible colors. So that's a decent amount of colors. And when you get into some of the compression later on, there's like some tricks to kind of do the similar type of colors with less.
What does the 2 signify there?
2 is like the binary system.
Oh, okay.
So 0 and 1, right? So let me step back a second, right? So remember I was saying like, if I have like 1 bit, there's only 2, right? It could be 0 or 1, right? If there's 2, that means it's 2 squared, 2 to the 4, 2 squared, which is 4, right? So 0, 0, 0, 1, 1, 0, 1, 1, right? And then 2 to the 3rd becomes 8 different things I can represent, right? So it's like 0, 0, 0, 0, 0, 1, so on and so forth. So you can see like the number of different things you can represent with the binary system as you add each character will go up exponentially, essentially, right? So 2, 0, 2, 1, 2, 2, 2 cubed, 2 to the 4th, 2 to the 5th, and so on, right? So that's why you have 2 to the 24th. It comes up with this pretty big number, 16, essentially 16 million, 16 meg. Okay. So one common thing you might say is, well, how much space does a picture take up, like a photo in this case, right? There's a picture, it looks like a hammerhead shark or something, right? So basically, you almost look at this like when you're doing your geometry, like your what's your length and your width. Oh, I moved the picture, right? So what's the length and width of this picture, right? But instead of the units being like inches or centimeters or whatever, it's pixels, right? So in this case, we're saying, oh, well, this picture, let's say for the sake of argument, is 479 pixels going this way, and then 332 pixels going this way, Okay, whether it really is or not, I don't know, but the idea is just pixels. You can think of it as a unit, similar to like when you measure your picture in terms of centimeters or inches or whatever. Um, that's what they're talking about here. So when they say 479 pixels by 332 pixels, they're kind of just saying the length and the width of the picture here, right? And then, of course, when you say, well, what's the area, right? That's just length times width. So that's why you multiply these two to say, well, these are the total number of pixels used to represent this picture, okay? And so then when I say, well, how much space is this going to take up? Remember what we said back here, how much space does each pixel take up? Okay, I must have typed over this before, right? So each, one for each, 3 bytes, okay? So a single pixel, remember, will have 3 bytes, right? One for each color, right? And so you multiply that, that's the number of bytes times these pixels to say how much space this would take up, okay? So remember each pixel is red, green, and blue, right? RGB, right? And it's represented by these 3 numbers here, okay? So you don't have, it doesn't really matter, right? It's like 51, 153, and 255, 255 being the max number here, okay? And so that combination will come up with these, it looks like this picture is like mostly blue, right? So these are just 3 numbers. It could be any one of these spots here, okay? And then, so each pixel is composed of 24 bits, right? Remember 3 times 8 bytes, right? And each byte is 8 bits, right? And it's saying that here, right? 8 bits, 3 colors, okay? And so that tells you that, well, we have the 24 bits here times the 159,000 pixels, right? And this tells you in terms of bits. Most of the time we don't talk in terms of bits for your space usage. We're probably talking in terms of bytes, right? So it makes it a little bit better there. So in this case, you know, you would just take this and divide by 8 to get you into the number of bytes that it takes up. Okay.
Professor, I have a question.
Yes.
So I missed this, but the 479 pixels by 332, that was the length and width, right? So if we were to like count length and width, that would be.
Yeah. I mean, is it literally 479, 332? I doubt it, but it's just arbitrary, right? I mean, you know, it's like I said, just think of it in terms of length and width, really.
Got it. Okay, thank you.
Yeah. So it's
I have
just
another question about that. Would
Yeah.
it be relevant for us to know, like, okay, 479 times 332, like, that's how big the image is, and then like convert it to bytes?
yeah, you'll get a question like that for the exam.
Okay.
So if you have to take a picture of this, or I mean, I'm posted this up on the Canvas site, right? If you, this is like an example, like kind of try to work it through. If you can follow the example and you can kind of do this calculation, you're sure to get a question on this for the exam, right? And I don't want to like constantly be like kind of teaching to the exam, but I feel it's only fair for me to point out that, you know, everything that I'm putting up here will be on the exam. So, you know, if you need something to help you, point you in the right place to study, you know, I do try to highlight it, right? I'm not necessarily trying to teach to the exam, right? That's probably not the right thing to do. But I will point out that this will be on the exam, okay? Yeah, so remember what I said, black is the absence of light, right? So you can see this, right? It's 0, 0, 0 all the way across, okay? And so you notice what they've put here, right? They've put it in binary, right? And then they put it in decimal and they put it in hex, right? And you can say, well, okay, maybe that's why, we kind of have you doing like these type of conversions and whatnot. But I'll be honest with you, like in this day and age, remember we talked about the point about abstraction. So you probably know we have any number of like website builders, all kinds of tools to just like a calculator, right? It just kind of saves you from doing that type of work, and it still gets the job done, right? But you still like to understand how things work, right? So just like in grade school, we don't just give you a calculator and say, okay, if you need to add any arbitrary number, you just punch it in the calculator and then that's it. There's the answer, right? We do try to make sure you understand what's actually happening when you do addition or whatever before we give you the calculator and say, do whatever you want on the calculator. So by the same token, these binary, decimal, and hex representation, although in practice, when you do a website or you do whatever, you're probably not going to be doing these conversions, right? You're not even going to be saying these numbers probably, right? But having you understand it before you can kind of use the tool is helpful. It makes you understand things so that if you had to go in there and tweak it and customize it a little bit, you could if you wanted to, okay? And you'll see more of this when we get into like designing web pages and stuff like that. So this, from a binary standpoint, obviously this is what the computer cares about. The computer is going to read this in, and this is what they're going to look at and convert that into the light that goes through the pixels. Okay. Chances are on the web page, when you're like specifying a color or something, you'll be doing it in decimal or hex, right? Very rarely you're going to be doing something like this in binary, right? That's really for the computer. And what happens on the web page, ultimately it will get converted to something that the computer will understand, right? That's why you're not really putting in binary. So this is just for you to understand. And so regardless of which one of these you represent, 0 is a 0, right? So all these are zeros here, and zeros here, and zeros here, right? Binary, decimal, or hex, right? But going to the point where we said before, right? If you were really writing this, you wouldn't want to write like a gazillion zeros like here. You want to be looking at these type of numbers here, right? So that's why you have something like a hex usually to represent these characters, whereas the computer doesn't care about that. The computer cares about just these zeros here, okay? Now the flip side of black is white, right? And so you can see all the max values here. So this is 111, and then you can see these are 255, 255, and 255. Now, one thing that kind of trips people up sometimes is like, oh, well, I'm representing 256 characters, so why isn't this number 256? The reason why is because you start off with 0, right? So 0 is the lowest number, not 1, right? So when you start off from 0 and I tell you that you can have let's say we start off from 0 and I tell you can have a maximum of 8 characters. That doesn't mean you go up to the number 8. That means you go up to 7, right? Because you start from 0 and up to 7. In this case, we're saying you have 256 maximum characters starting from 0. Therefore, the maximum is 255. So I'm telling you this because you might get something saying, well, okay, what is white in decimal, right? And you know that the maximum is going to be 256 characters because it's 8, 2 to the 8. You might be tempted to put 256 here. So don't do that. So do 255 because you're starting from 0, okay? And you remember from hex, what's the maximum character for hex? Is F, right? So that's why you have these 2 Fs here for the red, green, and blue, okay? So now with this, well, it's telling you it's decimal, which is fine. So, I mean, it's a quick test for you. It's kind of give you a quick hint here, right? Remember, this is red, green, and blue, and they kind of really remind you by making it actually the color of red, green, and blue. right? So if I give you 0 here and 0 here, which is 0 for red and 0 for blue, and I put maximum color 255 on the green, you don't have to answer me. Just, you can think to yourself, well, what color would you expect that to be, right? I hope it kind of seems obvious that it should be green, right? So that's what happens when you have like this with 0, this with 0, and then this becomes green. And as you can imagine, as I start to mix different colors in here, that's where you start to get, different color combinations. Okay. Now, but if you keep all the numbers to be the same, like this case, right? 255, 255, 255, right? But let's say I chopped it off by 55. I said 200, 200, 200, right? Or I said 10, 10, 10. So I'm kind of coming in with equal intensities across the red, green, and blue. And that's why we're talking about going from 0 or black to 1, which is, I mean, 255 for full intensity, which is white. Like there's shades of gray in between. But when you start to mix the colors up and down, let's say from the red, green, and blue, they're different values. That's where you start to get like different colors. Like look up here at the top, you can see how, I keep on hitting my mouse here. You can see, look, there's a yellow here, right? When you, I guess it's kind of yellow, right? When you're mixing a color at different levels there, but when you keep them constant all the way across the red, green, and blue, that's where you kind of get these different shades of essentially gray from the white to the black, let's say. Okay. So, all right. So we kind of went through like how each of these pixels, you add up all these pixels and they become a picture, right? And it's these combinations of these different colors here, right? So now that you have stuff stored on a computer, digital, right? It's much easier to do all kinds of digital enhancements, right? So like special effects, right? So like on your phone, right? I mean, almost all of you probably have like probably the latest and greatest in phones, maybe, I don't know, right? But any halfway decent phone taking a picture now, and with the app that's on top of it, it does all kinds of crazy stuff in terms of effects on the videos, right? I don't even know, like these days, like, is there such thing as people getting like red eye, right? But back in the old days, when you took pictures, like it was very common for like all kinds of like things like red eye and crazy stuff like that. And now, like with the pictures that the cameras are taking from the phone, let's say, it's almost like automatic. It automatically makes everybody look better, right? So it's doing all kinds of stuff, makes people look skinnier, makes people like, no red eye, like whatever it is, right? Even Zoom, right? Zoom does stuff to kind of make people look better too, I guess. So you have all kinds of information that's represented digitally, and it just becomes like a mathematical thing to do all kinds of different things, make the picture brighter, improve contrast, in this case, like red eye removal, imperfections in the picture, right? I guess the latest Android does things to like, actually remove people from the pictures, like for you automatically, right? So whatever effects you can think of, it's so much easier once it's represented digitally compared to what it used to be done when it was, on film and analog and whatnot. Okay. So, so what's the common thing, especially I guess at the beginning, like where you guys are coming in on this, is the idea of like being able to play around with like brightness and contrast. Okay. So brightness and contrast, brightness, you can imagine, like I was telling you, like when you get to that bigger number, the color is more intense, right? So that means you're making it brighter. So you can imagine if these are all numbers, what would you do to make something brighter? It's almost just like what I call a shift, right? I don't think the book refers to a shift. They just say, do plus 10, plus 20, plus whatever number you want to do to make it more intense and therefore make it more brighter. Okay. So this is the key point here, right? Brightness refers to how close to white the pixels are, right? I kind of refer to it as being more intense, right? Because white is the most intense. But this is how it's being described here, how close to white the pixels are, right? And so, like I said, if you look at this, if you're applying a formula to all the values for all the pixels in the picture, because obviously you're not going to go in there manually and do it one pixel at a time. You're going to just apply this general formula, and the general formula would be like shift everything plus 10, plus 100, whatever, and that will make it brighter. Okay. Now the contrast, what is contrast? Contrast, you can look at that as how sharply you differentiate between the darkest and lightest portions of the picture. Okay. So you can imagine if you like play around with the different, I'll call them delta, the difference between the dark and the light, that's going to be adjusting your contrast, right? So we'll talk to that in a second here. So going back to brightness here, see what it says here? It says add 14 to each pixel, right? So we want all the pixels to be more intense or brighter. So it's just across the board, every single pixel, we're going to do an add 14 to it. Okay, so they just took an example pixel, like whichever pixel, and it's 195, 195, 195, and it became 209, 209, 209, right? And you can show this little square here. You can see it went from like sort of this darker gray to sort of like a lighter version of it. Okay, it's hard to tell with this, with the black, you know, it was at 22, 23, 24, then you add it, it became 36, 37, 38. I guess if you look very closely, it looks like it kind of got lighter. It looks still pretty dark to me, right? But you know, it's only 14, right? If you add it more, I guess you can tell more. Okay, so you can see here's the original picture, and then here's where it become a lot brighter. Okay. So when I was saying shift, that's like across the board, every single pixel gets shifted by 14. Now, when you look at contrast, you're not really, you know, looking to be doing like a uniform shift, let's say. You're kind of like adjusting the spread. I call it the spread between the low and the high. So this is what they're putting down as the strategy for that, right? So for the smaller, for the darker pictures, the darker pixels, they're shifting that a smaller amount than for the lighter pixels. So it's a little bit more advanced formula here, right? And you can see like the before and after here. Okay, and I'll bring it back to the last one. So you can see what happened here, because I applied a uniform shift to all of this. It kind of just like really brightened everything up across the board. It doesn't really look that great, right? It looks, I don't know, maybe it looks kind of better, I guess, but it looks like really like overdone here, right? So I wouldn't look at contrast as the opposite of brightness. I look at it as maybe a refinement on it. Okay, so look here, you know, on the lighter pixels, right? It shifted it a bit more, and then for the darker pixels, it kind of shifted it less, right? Because maybe like here's his dark suit here, his black suit, right? You don't necessarily want it to become like super bright, because then it looks like his suit is like washed out or something like that, right? But you know, some of the other areas like his shirt or whatever, you kind of want that to pop more, right? So that's why we came up with this thing to say the larger amount of shift for the light pixels and a smaller amount of shift for the dark pixels. And that's why you would say maybe this enhancement of the picture looks better than this one. Okay.
Professor, I have a question.
Yes.
When you say add a smaller amount, do you mean like the numbers get like decrease.
So you see, I add 14 across the board for this one, right?
Mhm.
Yeah, and so so actually this kind of does it a little bit here, right? So, it's showing here where you can see the number here is 195, 175, 205. That's like a more intense or brighter picture, right? So here they added like 13 here, it looks like, from the 195 to the 208. So they added like that much more here, but look here, you can see like, so remember the lower number means closer to black, right? You can see, well, here they didn't add anything, right? Here they added like 2, and here they added 3, right? So it's a much smaller addition, right, for the dark versus like what they added here for the light, okay? And in fact, in this case, they didn't actually even do it constant across each color within the pixel. But the idea is like for the darker pixels, they added a much smaller number, right? In one case, they even only added 0, right? And then for the brighter colors, or the more intense colors, I can say, they added more to it, right? So the it wasn't I keep on coming back to the idea of a constant shift, right? If it was just a general brightness, they would just apply that uniform across everything, by, let's say, 14, make it more intense, okay? So that's kind of like how they applied this to improve on the contrast, okay? So instead of like everything kind of moving in parallel, going up or down, if maybe you want something to go darker, they're kind of like making the range either smaller or bigger, right? So that's how you adjust the contrast, right? So let's say the value between the lightest pixel and the darkest pixel, in this case is 239 to 38, right? When you're playing around with the contrast, that can either go up or down, like 239 minus 38, right? Maybe it goes bigger or smaller, right? Whereas if you're doing the brightness, it would be the same across the board, okay? So the next aspect to this, right, this happens to be a black and white picture, is they're playing around with color, right? They're adding some color to this thing, okay? And because you're doing red, green, and blue, that shouldn't be too bad, right? So remember what I was saying, if you kept everything constant from the red, green, and blue, you're playing around with shades of gray, okay? But you can see here, right? Forget for 1 second, just forget about these highs, mids, and shadows here. And you can see they're kind of applying different values within the red, green, and blue, right? So in this case, they're adding more red, and then keeping the green constant, and they're darkening up on the blue, okay? Or lessening the intensity of the blue, okay? And so they're doing different numbers, whether it's red, green, or blue, okay? But, the picture is not a constant color, right? So the picture it's not like all black or like all white or something like that. There's like this range, right? So that's why, they break it up into chunks here to kind of make the application of the colors, particular to certain ranges. So, right, they happen to choose or identify like shadows as this part here, and then they have the mid-range here and the highlights here, okay? And then, based on that range, they'll apply these values to shift the red, green, and blue within those ranges, Okay, and so they're pointing to different areas here, right? So the highs is essentially something like his white shirt, right? And the shadows would be something like his darkish color suit, right? And then the mid-range would be, you see kind of in the background is somewhere in between the dark and the white of his shirt, okay? So when you apply that type of shift, you can see it went from this to something like this, okay? In actuality, I don't know if it's 100% like this to this, because you see like these little dark spots here, here and here. They magically disappeared over here on the right side. So I think, think more in terms of like the general idea, like these little blemishes here. I think they must have did some other stuff to knock out these blemishes here before it got to here. I don't think that's really the point here. The point here is like just making like the suit, like, I guess it's looking a little bit more like blue here, and having like the white still, pretty white here, and then having this background like this with these colors in the shift here, okay? So that's the idea. I wouldn't say that, just applying this magically went from this to this. I think there's some other stuff that happened to kind of clean up this picture a bit, okay? But that idea is that to make something color from a black and white picture is you're coming up with varying shifts of the red, green, and blue, okay? So hopefully that wasn't like a long-winded explanation to get to the idea here, okay? All right, so digitizing sound. I don't know if you remember from your high school physics, right? But you have like sound waves, right? It looks like waves going up and down, and you have like a frequency of these waves coming across, right? So that's what this is describing here, right? So an object, creates sound by vibrating, right, and pushes the air, right? So these vibrations push the air, causes these waves to come across to hit your eardrums. Your eardrums, like, go back and forth and then convert that to a signal in your brain, and then that's how you recognize that to be a sound. Okay, so if I look at a sound wave, probably if you remember from your physics class, it would look, one portion of it would look something like this. Okay, and so as a computer, if you're trying to record this digitally for your computer, you can imagine like we're basically taking slices in time and trying to figure out a way to accurately be able to reproduce that wave, that sound wave. You see this here, right? Now, however many times I sample that sound wave, the more I do it, the more accurate or the more smoother that curve will be, right? The more better it would sound, okay? So you can see up here, if I only do a couple sample, which is what they call low sampling rate, you can see how kind of like blocky or edgy the wave looks. It doesn't look that smooth, right? And then when I do a lot more sampling, which is what all these lines are down here, which is what they call a high sampling rate, then you can see the curve looks a bit smoother than this. It looks less harsh, I can say, right? It's just smoother, right? So that's what they mean by sampling, okay? And so of course, like from a picture that you can see, this is still fairly low number of sampling, right? Typically, you're looking at something like this, right? In this case, 44,100 hertz, okay? So like how many times you want to sample something, the more you sample it, the better resolution that you get, okay? Approaching infinity, right? So of course, there's a space consideration here, but honestly, like when you look at sound, it's not nearly as much information as what you have to capture if you're looking at a picture or a movie or something like that. But still, you do want to try to be optimal. You want to kind of capture the right type of information, the right amount of information to accurately reproduce the sound for human consumption. Okay. So, basically you can imagine there's like a recorder that just like snapping every time, the sound is playing. Let's say it's a music for whatever, like a song or something is playing. And you can imagine there's something that's just recording every single second, right? Actually, it's actually much finer than that to store into digital format. And the idea is to actually reproduce these sound waves. Okay. So that's what the sampling is, okay? So this is important, right? There's a rule for how many times you should be sampling. Like I said, theoretically, you could be sampling to infinity, right? Like super fast type of sampling there. You could be doing a huge amount of it, but you might say, well, beyond a certain point, it kind of doesn't matter, right? And so this is the point here, right? Like humans, most people generally are going to listen or be able to hear sound about 20 hertz to 20,000 hertz to 40,000. Well, the maximum was 20,000 hertz, right? And the Nyquist rule says that you want to sample twice as fast as what humans can hear up to. So humans can actually, I stand corrected, humans can hear anywhere, I think, from 20 hertz on the low end to the high end is 20,000 hertz. So you want to sample 40,000 times because that's 2 times the maximum, 2 times 20,000. Okay. And that's all the Nyquist rule is saying, right? How many times you should be sampling for whatever you're recording for. In this case, we're recording for humans, but maybe you're recording for dogs or something, right? But let's say you're recording for humans, then you're looking at 20,000 hertz multiplied by 2, which is 40,000 sampling, okay? It's a simple rule, and you're definitely going to see this on exam, and it's simple enough. You just have to say, okay, what's the high end you have to go for, and then you multiply it by 2, right? Most of the time they're talking about humans, so it's 20,000 hertz at the high end times 2 for 40,000 sampling, okay? All right, now we just talked about how many times you're sampling, right? How frequently you're sampling to get that accurate sound wave, but it's not exactly the right analogy, but let's say each of those samples, I'm kind of taking a picture of that point in time. Essentially how much resolution do you have, right? And what do we call that from a sound perspective? It's this idea of bit depth, okay? B-I-T-D-E-P-T-H, right? So you remember like the sampling is going up and down, right? So here's the sound wave going across. The sampling kind of shows you how the samples are going up and down. I guess it's the amplitude of the sound wave, right? So, it's going up and down, and you're taking all of those samples there. Now, when you look at the bit depth, it's actually the other angle, right? It's going horizontal, right? Before it was going vertical, right? Before it was this. And to recreate each of the points relative to this axis here, going up and down, that distance, you're measuring that as part of your sample, right? The bit depth is going this way, right? Going the other way here, right? So again, the more bit depth that you have, the more accurate is that sound, okay? And again, it goes to the idea of going to infinity again, right? Unlimited number of bits, which, yeah, it's unnecessary, and you need to have a limit somewhere. It doesn't really go to infinity, right? But the idea is still the same, right? The more bits that you use, the more accurate that measurement is, okay? So this is like just a fact, I guess, right? Just saying it's using typically 16 bits. Okay. So that kind of shows you, right? So you can see here, right? This is like the lower bit depth here, and you can see the units, right? It's going up to here like this, right? And then you can see like the higher bit depth here. You can see like there's more lines here. So therefore, quote unquote, more accuracy going along this axis here. Okay, axis, right? So here, so this is a digitizing process, right? So this is like, your sound waves are coming across, right? And then it's getting picked up by this microphone, right? In a similar way, if there was like a sound wave hitting your eardrums, right? In both ways, like the sound wave is coming across something that causes that thing to vibrate, right? There's something like that inside the microphone, similar to your eardrum, okay? And then it's taking that and converting that to digital information. So that's why there's like this little box here that says analog to digital. And then over the wire, right? Yeah, let's say there's a wire from here to here, you see a whole bunch of these zeros and ones that will be coming across, or the signal, right? Signals will either be up or down, all right? And then when it comes out the other side, there will be something that will be able to translate these digital information and cause something to vibrate, like maybe your speaker, right? And then your speaker will generate those sound waves, right? Kind of almost similar to like how a telephone might work, right? So this hardline telephone, it would just take the input, create it to zeros and ones, and then come out the other side and goes into a speaker that generates a sound wave, which again goes to your eardrums and then makes sounds for you to listen to, okay? So that's what all this text up here is describing, is what I just described down here, okay? So, similar to like what you did for the pictures, like once you have sound represented digitally, you'll be able to do special effects, right? Different things to kind of clean up the sound, make things sound better, right? So, in recent times, very popular with music and whatnot, you have auto tune. Filtering out different imperfections, miscellaneous sound, I guess you can call it, and you want to filter those things out. Removes waves that are too high, too low for humans to hear. I don't know if that's advantage or not, right? I mean, it doesn't matter, you can't hear it, but you can do that, right? And that maybe just kind of saves a little bit of space. So, but again, the point here is you can apply formulas to change the sound to come up with different effects in a similar way that we were just doing with pictures. Okay. So when they talk about video, I think the easiest way to think about video is just a series of pictures, right? So I don't know if you ever did this thing where you kind of like come up with these on each piece of paper. You just draw the picture and then you kind of flip through the pages really quick, and it kind of simulates some sort of motion. Like, that's essentially how videos work, right? It's just a series of pictures. And so, you just put all those together and then you have some sort of video. In this case, you're talking about movies or whatever, right? So whatever calculations you did to calculate the size of a picture up here, like whatever calculation you did here, you just think of it for a video. You just say, well, how many of these pictures do I string together to make that video? And then it's essentially your third dimension. It's another dimension here to come up with how much space the video will take up. Right. So in some ways, I kind of look at videos as just a extra little bit of information on top of like a picture. Okay, so you would have done this calculation, right? Here, remember the pixels per frame, right? The length and width thing, right? So 640 by 480, right? So that tells you essentially the area of the frame. Okay, the frame is the picture. Okay, and then this will tell you how many bits there are, right? Remember, there's 24 bits for each pixel, right? So you take the number of pixels, which is this 307,000, times 24 bits for every pixel. And that tells you how many megabits there are for every single picture or frame within this video, okay? Now, when they talk about the bit rate, they're basically saying how many pictures am I showing over that certain time period? In this case, they're talking about a second here. So you're taking these number of megabits per frame, per picture, times how many of them you did in a second, which in this case, they're saying is 25, okay? 25 frames per second, right? And then you come up with 184 megabits per second. That's how much space it takes up for 1 second of video, okay? And then in this case, well, this video is taking up 3,600 seconds, right? So then you take 184 megabits times the 3,600 seconds, multiply all that out, and you end up with essentially 82 gigs, okay? So for those of you that look at your videos, you know, at home, and you might have like something on the director, you might see how big they are. Probably most of you have not seen any movies that are 82 gigs in space, right? They probably take up, I don't know, a few gigs, maybe 10 gigs, maybe 15 gigs at most, right? Like a Blu-ray or something like that. So that's why you kind of get into compression and whatnot, okay? So the key thing with compression, try to remember is, oops. Let me close this sucker here. Two concepts here, lossless and lossy. Lossless means that after they compress it and you restore it, you lose nothing, right? When you do compression, sometimes you do these tricks, but then you're not able to get to the original quality of the picture. You know, you lose something, right? And ideally, we don't want to lose things, right? But you can get more compression by doing these tricks to have lossy compression, right? And so when can you get away with lossy compression? Maybe it's when you're kind of squeezing things down to look on your small screen of your phone or something like that. You don't need to have like, you know, crazy, you know, high def that is meant to be, you know, done on a big screen TV, because you're only looking at a little screen, right? So that's where it might be appropriate to have lossy compression to save a lot of space, because the output is only viewed like on, let's say, a small screen or something like that, right? But in other cases where you're trying to present this high res movie, let's say on a big screen, well, then you probably don't want to have, you know, some losses in your compression. So that's why you have lossless compression also, okay? So the audio compression here, one quick thing is like, yeah, take away the sounds that are too high or too low for a human to hear, right? You strip out that and you save space there. When you look at videos or pictures, what they try to look at is, you know, do you adjust things on the brightness, kind of use less granularity on the brightness? But it turns out that people are pretty sensitive to changes in the brightness, okay? So usually you try to preserve the brightness of a photo when you want to do the compression on it. But, you know, remember we said it was like 16 million like shades of colors there. People are a little bit less sensitive to small changes in color. So instead of using all 16 million different colors, you might kind of compress that a little bit and use less variation on that. And that's what they call chrominance here. right? So if you want to do compression for sound, worry about the high and the low. For pictures, don't do too much with the brightness, but do what you can in terms of reducing the variations in color, i.e. chrominance here, okay? All right. Sorry, this class went a little bit longer, so I guess I'm gonna have to catch up with on the rest of this for next class. Sorry about that. Anyone who wants to stick around, I can answer questions and whatnot, and I will finish up these slides for next class. Okay. So I'm gonna stop sharing now. Again, I kind of hit the end of class. I hope not to do that next time. Okay.
Thank you.
Professor, can I ask you a quick question?
Have a good one.
Thank you,
Okay.
Professor.
Yep. All right.
Can I ask you a quick question about the extra credit?
Yes.
So I just put my answers in a document, but then
Yes.
I showed all my work on paper and pencil. So can I just send you the document along with pictures of the work I did? Is that
Yeah,
okay?
yeah, that's fine. No
Okay.
problem.
And you said you didn't want it as a Google Doc, right? It has to be PDF or Word doc or something.
Yeah, I mean, that's just to kind of prepare you for doing this as an assignment.
Okay.
Yeah, because the TAs are not going to look at it as a Google Doc.
All right. Okay. And I can just send it to your email, correct?
Yes, that's correct.
All right. Okay. Thank you. Have a good night.
Good night.
Thank you, Professor. Have a good night.
All right, good night.
Professor, I had a quick question about representing hex in RGB form. If F is the highest way that we can show hex, why would it be FF?
So it's so remember we're looking at 8 bits to a byte there, and there's 2 bytes, 3 bytes actually on this. So let me go back to sharing this screen here again. So let me come back up to here. Where is it? Okay. All right. So if you look at this, let's say this case is FF, right? And this goes over to here at 255, and then ultimately it's down to here, right? There's 8 of these bits. Remember, I was saying there's 8 bits into a byte. So these first 4 right here is 2 to the 4th, right? Which gives you your 16 characters. So that's why you have the first F here. But then you have the second 4 here, which makes up the second F here. You know what I'm saying? Forget about this decimal here for a second. Just think about this hex to binary here. So each of these are basically, they break it up, or you think about it in terms of 4 bits here, right? So there's 8 bits. Within the 8 bits, you break it up into 2 groups of 4, and 2 to the 4 gives you 16 different characters. Does that make sense?
Yeah, thank you.
Yeah, okay. All right, cool.
Professor, I have a quick question.
Yes.
I sent you the extra credit, and you said you validated I sent it to you. The only thing is on the bottom, I didn't put the honor code. Should I have that or no? Should I resend it?
No, for extra credit, it's fine. Just worry about that when you turn in the assignment.
Yeah, I make sure to do that. I wasn't sure for this one because you didn't specify.
Yeah, no, I only give out these extra credit things as really just practice for you. I'm not even really correcting it, right? Some of them I do a quick eyeball of it and look at it. Some of them are quick for me to look at. But I have a ton of people sending me extra credit, right? So I'm not really, trying to go through and grade it. I just look at it. I put out some reminders and tips for people just to help them for the exam. And that's it.
Okay, thank you.
Okay.
Have a good one.
You too.
So is the extra credit based on completion rather than accuracy? If you tried your best.
Yeah, I mean, at the end of the day, it doesn't really hurt me whether you get it right or wrong. It's more like if you don't understand like how
Yeah.
how to come up with the right answer, you're gonna have a problem for the exam, right? The only purpose I give you the extra credit is for you to practice for the exam.
Got it. Okay. All right. Thank you.
All right.
Professor, I had a question about converting binary to hexa.
Binary to hex. Okay.
I had a question about showing like the work. Like
Yes.
just use the chart or like
Yeah, I mean that's what I would do. I know that's not really like anything mechanical to it. It's just looking at it from a mapping perspective. But usually what I've done when I was doing this stuff was I would just kind of say, well, here's like the 16 characters, right? Because there's only 16 characters for hex, right? And just like what I showed before, where they show like the two groups of 4 bits there, then I could just look at those and just map that. And then I have my hex conversion.
I see. So would we get the chart on like an exam?
You'll get the ASCII chart, but you won't get the hex chart, or I wouldn't count on it, right? So just, there's only 16 of them, right? So just know that you can have like the 4 bits and just say 000, 001, 0010, 0011, and so on and so forth, right? It's just like adding 1. It's almost like I tell you to write 1 through 10, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? So you kind of do that with the bits, and then just write 1 through 9, and then A through F, right? And that's your 16 mapping there.
Okay.
Yeah.
Thank you.
No worries. Cool.
Oh, sorry.
Yes.
I had a question about chapter 2, not about anything we learned today. What exactly from chapter 2 will be tested? Chapter 2 is the human computer interface.
Yeah. So if you let me share my screen again. So if you go over to here, here, modules. So within the modules, so they kind of lays it out pretty well here. And where it says like the vocabulary and the textbook questions, I mean, sometimes like the stuff that's on the exam is like kind of taken straight from here, right? So this is pretty accurate in terms of what will be on the exam, right? So if I ask you like, what is feedback? Remember I was saying like, you can see like the little hourglass or something like that to kind of tell you that something's working on the computer. Like an instance here would be like, let's say I have like a Word document that I say, you know, new, right? New Word document. That's considered like a new instance of that document, right? Remember consistent interface, right? So I was like, maybe Microsoft Office, you have like Word, you have PowerPoint, you know, the common functionality, it all kind of works the same way. Copy and paste works the same way. So consistent interface, why do we have consistent interface, right? Metaphor, right? What's like the touch metaphor, right? And there's a decent amount of time we spent about like the desktop GUI, right? Looking at that, the desktop as a metaphor. You know, does that make sense?
Yeah, it does. Thank you.
No worries. Okay.
Hey, Professor, I was
Yeah.
wondering if the material and terms discussed in the textbook but not in class is going to be on the test, because I'm confused as to how much emphasis we should put on the textbook.
Yeah, so like I was saying earlier, when you look at the textbook, the lectures, and the recitations, they sort of complement each other. It's not like whatever we cover in lecture will go word for word and match up everything to the book. Otherwise, you wouldn't have to read the book. And likewise, you maybe just read the book and don't have to come to lecture or the recitation. So in some ways, there is some overlap to maybe emphasize certain key topics. But in other ways, the recitation, the lectures, and the book are meant to complement each other and not overlap. So I think when you look at what I just shared in terms of the modules and shows like each things that you should be looking at, I think that's a pretty accurate representation of what should be on the exam. And there's some things that I'll cover in lecture where I'll specifically say, hey, this will definitely be on the exam. These are important things. Does that make sense?
Okay, thank you.
Okay.
But there are like some terms in the
Yes.
textbook that are defined, but like have never been mentioned, or I guess like not in the
Yes,
the
that will be true. So yeah, we're not gonna, I'm not gonna cover every single term that's in the textbook.
okay.
Yeah, but if there's something in the textbook that you don't understand their explanation of it, then just let me know. And then I can certainly cover it with you, let's say during office hour, or you can send me email or whatever.
Okay, thank you very much.
No worries.
I'm just gonna assume that's the end of the questions. I just wanted to stay to hear the questions like usual.
Okay, no worries.
All right, thank you, Professor.
All right, have a good weekend.
You too.
Okay.
The same goes for me. I just like to sit and listen.
All right, no worries. I understand.
Yeah, I'll see you next week.
All right, see you
Virtually
next
this
week.
time.
All right, cool.
Bye.
Bye. Mhm. Okay. Neha, you're all right?